Good morning.
No, it's not on.
Good morning. Can you hear me? Yes, good. Good morning and welcome. My name is Perry Hoffman, and I'm president and co-founder of the National Education Alliance for Borderline Personality Disorder. We're an organization that was started about 7 years ago by family members, consumers, and one mental health professional. And our mission is really to build awareness on this often devastating disorder. This conference today is a really groundbreaking conference. There's never been a conference before that's devoted one full day to genetics and borderline personality disorder. So we're delighted that you're here today. We also invite you to go on our website, www.borderlinepersonalitydisorder.com, where you can not only review online this conference for the full day. We're taping it, or video and audio taping it, but you can also listen to 35 other conferences that we have posted on our website. So before I turn the day over to Dr. Joel Silverman, I do want to thank our presenters who are here without pay. They're giving their own time to try to promote education and information on borderline personality disorder. So thank you, Dr. Kendler, Dr. Gunderson, and Dr. Friedel for all that you're doing to help promote our work as we try to get more information out on this disorder. Thank you.
Good morning and welcome to all of you. My name is Joel Silverman, and I chair the Department of Psychiatry at VCU. We have multiple missions, including research and taking care of patients and teaching. And as part of teaching, we're very involved in advocacy, and I will say a few words about advocacy soon. I really appreciate having the opportunity to partner with the National Education Alliance, because when advocacy organizations and universities come together, we can do some very good things. We're here to talk about what is most current in the thinking about borderline personality disorders. As far as historical context goes, if you go back 50 years, there weren't diagnostic criteria. And we didn't have treatment guidelines. And there weren't good science. There wasn't good science about genetics and biology. And we were confronted with people who were very distressed, and we had a little bit of knowledge, but it was very hard to figure out what we were trying to help and how to go about doing it. So there have been significant strides, and you're going to hear a lot about them today. Lastly, what I wish to share with you is that in the very best of times, it's still, unfortunately, difficult to advocate for our patients, to get adequate resources for them, whether those resources would be access to careful diagnosis, or access to treatment, or access to appropriate housing. And ladies and gentlemen, we ain't in the very best of times. So what happens in this kind of economy is the need increases because people are under greater stress. They've lost their jobs. They can't get their meds. They've lost their insurance. So the need rises. Alcohol, family violence. And at the very same time the need is rising, the resources are getting cut. Whether they're resources from an insurance company, resources for community mental health centers, resources for academic medical centers. So in these times, the requirements of the need for advocacy, the moral requirement for those of us who care to advocate, goes way up. So advocacy can go across a huge spectrum from saying something when you hear a colleague say, "Oh no, not another borderline," to going out and actually taking the energy to have breakfast with your legislator, or talking to somebody you know who could make a contribution towards some of the kind of research and thinking that you're going to hear about today. So these are not the best of times, which calls upon us to do infinitely more to advocate for the science, the patients, the families, and the field. So I hope you'll take that as a take-home message. It's now my pleasure to introduce to you my friend and colleague, Dr. Kenneth Kendler. Ken is one of the very few people I know in the world who has the right to be arrogant based on the incredible production of his career, who remains a very humble and gentle and modest person. It's been my pleasure to work with Dr. Kendler for decades, and right here in River City, we have some of the very best genetic science that relates to mental health and mental illness that exists in the world. So I would ask you to join me in giving Ken a very warm welcome.
Thank you for that kind introduction, Joel. Give me a minute to hook up. Well, good morning. Can you all hear me? Understood. Yeah. So a few introductory remarks before I launch into my discussion. First, I'm not an expert in borderline personality disorder. I have had clinical training in psychiatry in the late 70s and early 80s, and I certainly confronted a number of borderline patients when I was not a terribly mature clinician, and then I've had the experience, fortunately, as I have matured in my 40s and 50s, of caring for people with this condition. I was interested to see how much better 20 years of clinical maturation helped. But I don't begin to bring the kind of clinical expertise that you will see from the other two speakers here today. My main career and research focus has been in the area of the genetics and the epidemiology of psychiatric disorders. I have been very interested in the problems of nosology, about how our disorders sort, what genes do, and more recently, in this extraordinary molecular revolution of trying to actually track and localize the specific risk genes for psychiatric disorders. So when Perry first discussed this with me, and I think this was at the UPA in San Francisco, we met somewhere in bookshop, right? What we discussed was that my job here was first and foremost, to broadly introduce you to the field of psychiatric genetics, which itself is quite a challenge in this because the field's moving very rapidly, and this is a technical field. It's full of statistics, and it's full of molecular methods. So this will be testing both my pedagogic skills and your attention on this Saturday morning, because you're going to get thrown a lot of detailed information. Hopefully my job, don't get lost in this, and if you get desperately confused, there's a small enough group, we really have a fair amount of time together, please raise your hand. But Hopefully, I will be talking you through what the important conceptual issues are. But second, I have, through a wonderful series of collaborations with colleagues in the National Institute of Public Health in Oslo, Norway, been for about 6 years collaborating on a study that involves the first high-quality collection of personality disorder data in adult twin populations. And so in the middle of this talk, I will be presenting to you a series of kind of interpolated, think about a map, kind of small and then gradually expanding about what we have learned, really about the structure of the genetic risk factors for personality disorders in general and for borderline personality disorder. That'll be sort of in the middle of this stream of this broader talk about the nature of psychiatry. So that's the agenda for the morning. It always helps to have a framework. I have been pondering much about philosophy of science in the last 6 or 7 years. This is an effort to really think about when we say psychiatric genetics, do we mean one way of viewing the world scientifically? And I think the answer is absolutely not. That is, this is a series of somewhat interrelated and somewhat competitive paradigms scientifically, and I will be taking you through these as part of the talk today. The first, what I call basic genetic epidemiology, and here we study kind of old-fashioned genetics, families, twins, adoption studies. We use, in this case, some fairly simple statistics, and this kind of genetics asks really one simple foundational question. That is, how much does a disorder run in families, or how heritable is it? Really, it's where you have to start if you want to try to understand the condition. I will present and review very quickly where we stand with respect to those questions. Second, what I have called advanced genetic epidemiology uses the same techniques. What is critical here is genes are not directly measured. Instead, their aggregate actions are inferred from patterns of relationships among special kinds of relatives, identical twins, fraternal twins, biological parents who give children up for adoption, individuals who are step-siblings who share environments. But we don't actually go off and measure the DNA. We get aggregate results, but it doesn't tell you the biology. They use a kind of statistic that's here, but in much more sophisticated ways. And I will be showing you diagrams full of dozens and dozens of paths from a form of structural equation modeling that is used predominantly here. So the statistics can get, from my perspective, very exciting and challenging, but also hairy and sometimes pretty opaque. And here we're really trying to move beyond the simple goal of quantification to explore the nature and mode of action of genetic risk factors and how they interrelate to the environment. So of course what's exciting here is we're looking at things like comorbidity, development, how genes and environment interrelate, how things act over time. Questions that from a clinical perspective are much more challenging and reflect the dynamic nature of the risk factors for psychiatry as they develop over time. Now, when we come to gene finding, as they say in the movie, we're not in Kansas anymore. This is a very different kind of science. Now we are using very different kinds of data collection strategies, high-density families, but overwhelmingly now case control. We're using a completely different group of statistical methods, and now it's going to be full of high-technology terms of SNPs and GWASs and other things that we'll introduce to. Here our goal, not at all like these, is to determine the genomic location and identity of risk genes. So it's broadly within the rubric of psychiatric genetics, asking really quite different questions. And the final natural denouement of these efforts is really molecular genetics itself, which again is quite different. And here the task is to identify the critical DNA variants and then trace the biological pathways from DNA to and a number of groups across the world, ours to some extent, are trying to move from this domain to this. We have post-mortem samples. We're trying to study brain, animal models, and so forth. But I will not be spending hardly any time in this area here. It's still mostly a promissory note. A bit of advances, but mostly we're not there yet. So with that introduction, let's get going. So, basic paradigm one. What have we learned? We've learned that all psychiatric and substance use disorders that have been studied have been found in family studies to be familial and in twin or adoption studies to be heritable. That statement is really without exception. Generally, we have had quite good replication across the studies, and that's remarkable given the differences in diagnostic approaches, in sampling methods, in the countries that these studies have been done. So if the determination of a good scientific practice is the capacity to replicate, this kind of psychiatric genetics has really worked well. Third, and I think very interestingly, in the last 10 years, with the accretion of more information, mostly from twin studies, meaningful differences have begun to emerge in the levels of heritability across different disorders. Now, what is heritability? This is a statistic that is often misunderstood. First, it does not apply to people. It is a population-based statistic. It's only meaningful for a given disorder in a given population. I'll read the technical definition and then explain it. It is the proportion of individual differences in a particular disorder or trait in a particular population that results from genetic differences between individuals. Think of it as a ratio. The denominator is all the things that make people different for a given trait, let's say borderline personality disorder, or the vulnerability there too. The numerator are the genetic differences in that population that contribute to those, and the heritability is simply the ratio. It is 0 if genes make no contribution to individual differences. It is 100% if everything that makes people different for that trait is genetic, and it's somewhere in between, which it virtually always is, if some ratio of the individual differences result from genes. If we were all to step outside into the courtyard and line ourselves up from the shortest of us to the tallest of us, we would see that we as a group of human beings are very variable for height. We have studied this many times in all kinds of designs, and I can tell you that about 90% of the reason why you are the height you are, controlling for differences between men and women, is a result of the genes that you've inherited from your mother and father. If you're in a well-nourished population, you haven't broken a leg or had some spinal injury, the reason you're as tall as you are is almost entirely a result of the genes your mother and father inherited, or you inherited from them. Now, this is a summary slide. You can sort of argue at the boundaries, but what I've tried to do here is on this axis show you some sort of markers of heritability of things you might care about. Remember, it's very important to remember there are things that we care a great deal about as humans that run in families, like the language we speak and the religion that we affiliate with, that don't have anything to do with your genes. So it's important to remember that. We live in a slightly overly gene-centric world. Everything is not due to genes, fortunately. But you can see that in these traits, they range from things like height that are very, very highly heritable to things like myocardial infarction and breast cancer, which actually have only moderate genetic influences in aggregate in population. So what's of more interest to us is how do these disorders sort? And I would roughly suggest that we can divide the psychiatric disorders into 3 groups. One are the rarer high heritability disorders of schizophrenia, bipolar illness, and autism. And interestingly, these are as genetic as any biomedical disorder. In fact, it's hard to find a disorder in general medicine that is as heritable as schizophrenia, bipolar illness. Really doesn't exist. And I occasionally get reminded of that when I get in conversations, for example, on subjects committees, where some, and pardon the stereotype here, if there are any surgeons in the audience, but a surgeon says something like, oh, well, that's just a mental disorder. You sort of flip the hand like this, as if, it's not biological, it's not meaningful, this is not scientific. And at some points, I sort of want to whip out this, you know the genetic role of this compared to things you treat? You're claiming that this is really not a biologically influenced phenomenon. I usually restrain myself, but not always. In the middle, we have the substance disorders. And this really reflects a paradigm shift 20 years ago. These were largely viewed as a problem of moral turpitude or weakness. The evidence now is very strong, especially for alcoholism, the important genetic role. Now, I list personality disorders here. I'm going to show you some data that's partly true and partly not, so you'll have a more nuanced sense. But by and large, the moderately heritable disorders are amongst the most common, especially major depression, where genetic influences are important, but the environment also plays a very critical role. We'll be talking some about that today as well. So this is sort of a broad 30,000-foot view about the heritability of psychiatric disorders. That's all I'm going to say about paradigm 1. Let's now move on to paradigm 2, where things, for me, get considerably more interesting. So, one of the things that you can use twins for is to actually clarify the environment. It's often thought that genetic designs, of course, will help you clarify what genes are doing. It is rarely appreciated that they can be used in a converse way. I have been relatively preoccupied with the problems of causal inference in psychiatric epidemiology. So it is not difficult for us to show that trait A is correlated with trait B. It is sometimes devilishly difficult, especially since for many of the things we care about, we cannot ever do randomized controlled trials to understand the causal interrelationship. And just to start out as a first example, I want to use a method of twin designs of clarifying what is essentially an important environmental causal question, and that has to do with the interrelationship of the age at first alcohol consumption and the subsequent risk for alcohol problems later in life. The correlation is not in doubt. Many large-scale studies have shown that if you start drinking regularly at 12, 13, 14 versus 18, 19, 20, you are at substantially increased risk of having alcohol problems later in life. Now, there are many in the literature, and if you read those papers carefully, you jump to causal inference. That is, that it is that early onset of alcohol consumption causes the later drinking problem. That could be true, but there is a plausible alternative, which is that both of them are a consequence of some shared set of factors, like I don't like to do what anybody tells me. I like to cut up. I like to be deviant. I like risk-taking. And that there might not be a causal relationship. Now, is this an academic question, a pejorative term? But the answer is no. People have advocated for trying to move drinking liquor stores away from college campuses to try to prevent young people from having access to alcohol on the basis of the fact that they think this relationship is causal. Now, we're never going to do an experiment where we take individuals and randomize them at the age of 17. They never follow our instructions anyway, of course. So it's not a question that we're ever going to know experimentally. One way to get some causal traction on this is what is called a co-twin control design. We're all generally familiar, I hope, with the idea of a case control design. You try to pick individuals, one exposed to a risk factor, one not, who share as many characteristics as possible. Well, here the design is you do that, but you do that within twin pairs. And most especially, you do that within identical twin pairs. So it is commonly noted that you never live life twice, but the closest one will ever come in this universe is studying identical twins who have been reared together, because they got all their genes in common, shared mom's womb, shared the child environment, shared the community, shared the schooling until whatever age they were at which they moved away. So they are as well matched on a set of variables as anything you're ever going to find. Rather than go through the details of this rather complex slide, I just want to ask you to do the thought experiment. So now imagine that we start with pairs of identical twins, and they're hard to find. You have to study thousands of twins. But you'll find some where one twin begins drinking regularly at a substantially earlier age than his or her identical cousin. And then we follow those twins up into their 30s, and we ask the key question, does the earlier drinking identical twin have much higher rates of alcohol problems than the later drinking co-twin? That's the critical experiment. Let me show you what that data looks like. So this is in males. This is the average ratio. Early drinking people in our entire population in males are twice as likely to have alcohol problems when they grow up. We're just repeating the other observation. If you look within identical twin pairs, it's a non-significant difference. Within females, the relationship between early onset drinking is much stronger, fourfold greater. Within identical twins, absolutely no difference. So let me just repeat what this tells us. If I have a pair of genetically identical individuals who've grown up together, if one of them drinks at age 13, one doesn't start drinking regularly till 17 or 18, and I'll follow them up into adulthood, there is no difference in the risk for alcohol problems between the two. That is inconsistent with the idea that it is in fact the early drinking which causes the later problems. It is entirely consistent with the idea that there's some common set of shared vulnerabilities that cause you to drink early, that cause you to have alcohol problems. And that, what is critical about this, if true, is that according to this model, you can do whatever you want, moving liquor stores 1 mile, 3 miles, 8 miles away from schools. When that person turns 21 and has got the predisposition, unless you completely make alcohol unavailable, he or she will find it and develop alcohol problems. Now, I actually don't want to convince you that this is true. There have been 2 other attempts to replicate this finding. One is absolutely consistent with this, one somewhat less so. My main point here is, again, a pedagogic one. We have key questions about environmental associations, and sometimes the way to answer those questions is to go into genetic designs. Really, that's the major point. All right, so let's now move on to what would be regarded as more traditional genetic epidemiologic questions. Here, and I'll spend a lot of time on this, this is the sources of comorbidity. So let me introduce you to a little bit of our terminology, our A's, C's, and E's. You'll be seeing a fair amount of this. A stands for additive genetic effects. Just think about it as the actions of genes. For 60 or 70 years, statistical geneticists have divided the environment into two kinds. And this actually goes back to laboratory experiments, where C reflects shared environment that makes siblings more similar to one another. For human beings, it would be things like the nutritional aspects that your mom provided, the psychological aspects of your home, whatever your community exposures would be, your social class, that you did or didn't live in an area that was highly polluted, any sets of things that makes people growing up in the same family similar. And E is the kinds of environmental exposures that make siblings different from one another. You might think of it as Prince Hamlet's slings and arrows of outrageous fortune. Now, the question underlying this is, do genes respect DSM-4? Have they read it? Do they obey it? Do they see it in that way? I'm going to present a series of analyses. The first, and this is going to form a rubric because we will be soon getting into the work on borderline personality disorder. This is a study that we did about 7 or 8 years ago, one of the first large-scale studies. This comes from over 4,500 complete twin pairs, all born here in Virginia. We were training interviewers, sending them out across the state. This was a very large amount of fieldwork effort aided by a number of talented colleagues and dedicated interviewers. Everybody was done blind. Interviewers were carefully trained. This is what the results look like. Let me try to walk you through this question. I think some of you in the audience will have seen this slide before. So these are 7 common adult psychiatric disorders. That stands for generalized anxiety disorder. Think of the following set of questions. On the one hand, is it possible that DSM got it right? That is, that there is distinct sets of genetic risk factors for each DSM category. That's one item. The other extreme is that there is no specificity whatsoever to psychiatric illness. All we have is one general dimension of screw-uppedness, and that all these names that we give them, we're just fooling ourselves into thinking we're pseudoscientists. There's nothing specific at all. And that has been claimed by anti-diagnosticians. So the answer to that question from these empirical results, there's lots of rigorous statistical stuff behind it that we don't need to go into, is that the answer is in between those. We don't find lots of distinct genes from any categories, but we find 2 uncorrelated underlying dimensions. The first dimension, this common factor here, has strong relationships. The strength, just the orange lines are the ones that are very strong, the white lines are weaker. That these 3 disorders, which those of you that do adolescent psychiatry particularly will recognize those as internalizing conditions, share a strong common set of vulnerabilities. And these externalizing disorders, alcohol, drugs, antisocial behavior and conduct disorder, share another set, and these 2 are effectively uncorrelated. There is a hunk of specific genes for drug and alcohol. I'll probably show you a little bit about that later, and that's very sensible given that when drugs are put into our body, we metabolize them, they act with neurotransmitter receptors and so forth. So this initial opening salvo of this discussion suggests that for this particular example, genes are not respecting DSM, but they're telling us something about broader underlying predispositions that by and large are not diagnostic. All right, so now let's get into the section on borderline personality disorder. All of the data that I'm going to be presenting, think about this as a kind of, well, I think you could say this is a diamond. It's such a lovely study that we're going to turn and look in different directions. So hopefully by the end, I will try to give you as complete a picture as I can. So this is a sample. This is, again, as is typical in Scandinavia. This is a birth certificate-based registry. It has lovely epidemiologic characteristics. Every one of these individuals was personally interviewed by either a psychologist or psychiatric trainee. We used the SID-P. I don't claim to say that the measurement issues are simple in personality disorders, and again, our other speakers are more expert in that than I.
But insofar, this was a sit-down, structured interview. This was not hours and hours of contact. This was not a psychotherapeutic relationship. So the results you're seeing are using good quality techniques, but there are limits to measuring personality disorders in this setting that you need to be aware of for all of this work. Sample size is pretty good, 5,000 pairs or better, but this is what we had to work with. We did examine every single one of the DSM disorders. So I'm going to sort of start small and grow big. So this is our first paper where what we wanted to do is to look at cluster B of the personality disorders. Those of you that remember your DSM, cluster B, sometimes called the dramatic cluster, consists of 4 personality disorders: antisocial, histrionic, narcissistic, and borderline. Now what this god-awful diagram looks like, and you will see ones that are worse than this, is how many genetic factors did we need to explain these conditions? And the key result here is that we couldn't do it with one. This common factor, which has these paths to the 4 disorders, has relatively strong contributions, but that did not provide an adequate fit. That is, we could not explain the vulnerability to all 4 of these dramatic personality disorders with one common genetic factor. And a second one had to be included in the model that had loadings only on the 2 of antisocial and borderline. We will see this again with a vengeance in a subsequent slide, that there is something about these 2 conditions that, from a genetic perspective, they're a close interrelationship. Now, for me, this is surprising and exciting. Surprising in the sense that those from a lay perspective regard antisocial personality as the kind of pathologization of masculine characteristics. Right? Impulsive, unempathetic, cruel, irresponsible. And borderline is sometimes criticized as being an exaggeration of feminine characteristics. So that these, in fact, would share a common genetic substrate is particularly intriguing. All right, so that's slide number 1 here. And just of interest, if we want to sum up the total heritability of borderline personality disorder examined in this one-off way, and I'm going to contradict myself in a moment, it's pretty modest, 35%, very much like what we'd find for major depression, generalized anxiety disorder. About 2/3 of that is the part that's shared with the other 4 disorders that are of the cluster B variety, and one is is the one that's shared with antisocial personality. So that's at least our first look at the fact that the genetic substrate for borderline personality disorder is complicated, but it's going to get a lot more complicated. All right, next question. When we calculate heritability, when you do any research, there is this thing that we call error, unreliability of measurement. It comes basically right off the top of any heritability estimates. If you're diagnosing a disorder and there's a lot of unreliability in your measure, that will cap and actually attenuate the heritability. We were concerned that these interviews, which obviously are interpersonal, we did some measurements, we did tape recordings, we were not sufficiently resourced to do full bore, have interviewers come back 3 weeks later. We were concerned about the reliability, that the correlation across 2 assessments, 2 interviewers, may be relatively moderate, 0.5, 0.6. In which case, we would actually be substantially underestimating the heritability of borderline or any other personality disorder because of the measurement time. How could we answer this question? We could answer it because before we did our study, Sven Torgerson, who has worked in this area, gave individuals a detailed self-report questionnaire that we were able to extract items from that, and this was 4 or 5 years before we did the interview, that did a pretty good job of assessing borderline traits. And any of you that have studied psychology, this is a classic attenuation for unreliability design. You basically measure something twice, and then you can calculate the heritability of that, which is stable between the 2 of them, and that really gives you a measure of the impact correcting for the error. And that's all that this design is. The error is down here. Now, the true error, and this effect now is the part that is temporally stable between these 2 assessments. And so what we found is that you've got to square the statistics the variance accounted for. That's now nearly 60%. So what this suggests, I can't claim this is definitive for a complex series of reasons, but it's consistent with the idea that one of the reasons why the heritability of borderline personality disorder, our assessment with this one-off
quite detailed interview was as modest as it was, is problems of reliability. That actually, if you could assess borderline personalities with perfect reliability and no error, you've really got a condition that's more like 60% irritable, not 30 or 35%. All right, so things are getting more complicated now. This was I'm going to be presenting to you two analyses, each of which were the result of between 6 and 9 months of work by our very talented team of analysts, particularly by Steve Ogden, who was as good a modeler as goes. And the amount of electricity and computer time we burned up in these analyses, I don't want to tell you about. This is a multivariate statistical analysis of all 10 of the DSM personality disorders. We had never gotten to run on our high-speed computer system models with more than about 8. So we were really pushing the frontier here. Some of these models took things like 50 to 60 hours of CPU time to run. And then, of course, they failed because some parameter was misspecified and we had to start all over again. But that's how science works. We're pretty sure these results are right. Let me frame this to you very much like I framed the prior slide, which is that, remember, there are 3 clusters in DSM. There is the odd eccentric cluster, DSM personality, paranoid, schizoid, schizotypal. There is the dramatic cluster we talked about, histrionic, borderline, antisocial, narcissistic, and the anxious cluster. So again, our question was, do we see 3 genetic clusters that map onto the way that DSM has previously organized the personality? Or do we see something different? And the answer here, like the previous one, is DSM. Genes are not following DSM at all. We do see, the only similarity is that we see 3 clusters, but they're mapping in very different ways. The first cluster has loading on all the way across the board. Again, here the most prominent ones are pictured in red, but notice that all 3 of the clusters are substantially loaded on this first factor, with loadings on paranoid, histrionic, borderline, narcissistic, dependent, obsessive, compulsive. Here is the factor that I showed you earlier, which is factor number 2 loads only on borderline and antisocial. So we are again seeing, even when you're measuring across all the 10 personality disorders, this signal is jumping out at you. This is something unique and robust about the genetic substrate for these 2 conditions. The third is simply introversion we discovered with loadings on dependent and schizoid. Now, just for a minute, let's bore down and look at the loadings on borderline personality disorder. So these are the 3. The biggest one, of course, so you'd say that borderline personality disorder, the biggest chunk of its genes come from this special thing, these special hunk of variants that it shares with antisocial. But it's got a pretty good loading on what is a kind of generic vulnerability to personality disorder. And it's got a modest loading on this introversion kind of component. So hold that in mind. Now I'm going to bore down even deeper by looking at axis 1 disorders and how they relate to borderline personality disorder. This is analyses entirely done by my Norwegian colleagues. So here this is a slightly different statistical method, but think of this as a regression, and we're trying to use 4 different genetic factors all to predict borderline personality disorder. So the question we wanted to ask was, moving away from the axis 1-2 disorders that we talked about, how closely in this sample of Norwegian young adults does borderline personality disorder relate to the externalizing axis 1 disorders of conduct and alcohol use, and then we bring in antisocial. So this loading here reflects what's shared between all of them. What's interesting is that we're accounting, I think actually it's going to be better if I show you the next slide. I'm getting through a lot of squaring. Yeah, okay. Let me just... This is the best one. So here I break down in pie chart form from that one analysis and one analysis only the proportion of genetic variants. So A1, this part is what's shared in common across all 4 of those disorders: conduct, ASPD, alcohol use disorders, and borderline. A2 is what is shared from the latter 3, antisocial, alcohol use, borderline. The part that's shared just specifically between alcohol and borderline, taking account of what's shared with antisocial and conduct, is ministry. So there's really not something very specific about the relationship between alcohol and borderline. It is captured by the broader relationships between externalizing conditions and borderline. And then we still get a hunk that's unaccountable.
This data is unpublished. The data I'm now showing you is very new. This is just under submission. This was about 8 months of work. Yes, please. I can try. Thanks. So this is statistically what they mean. A1 is all of the genes that are shared between the 4 disorders. It's the kind of biggest picture. So it's something that's shared across everything. A2 will be shared across these 3 disorders. A3 will be shared between those 2 disorders only, and A4 is only on borderline. Think about it as peeling back an onion, effectively. The top part is what's shared across this broad set of externalizing things, and then we're diving down, and the core is what's left that's specific for borderline and not shared with others. We're telling that by studying in a statistical model the predicted correlation between the genetics of these disorders. It's harder to articulate than that. This is a logic from regression analysis. So I think the onion analysis is best. That is, we're able, by comparing identical and fraternal twin pairs, to determine the role of genes. And now we're using those as a predictive characteristic. The goal here is to predict this thing. And we're really asking, how much can I predict from everything that's shared between these? How much can I predict peeling away conduct disorder? How much can I predict peeling this away? And then what's left at the end? Probably about the best I can do. Sit down and draw stuff on paper. All right. So this is about as bad as it gets, which is pretty bad. So there was a conversation at dinner last night about whether there is an axis 2 and should it be supported. This is, I think, to say, actually, the first time that we have been able to look at the genetic structure of all common axis 1 disorders and all axis 2 disorders. So this has been a very exciting opportunity. We just submitted this for review about 2 weeks ago. And I'm going to show you first the genetic structure and then the environmental structure. I'm obviously going to focus on where borderline is in this really complex picture. But again, let's take the big kind of bird's eye view here. We found 4 factors. One of them appears to load across internalizing axis 1 disorders pretty clearly. Part 2 appeared to load mostly on internalizing axis 2 disorders. I'm going to come back. Factor 3 appeared to be mostly externalizing axis 1 disorders. And factor 4 appeared to be externalizing axis 2 disorders. Now, there are a lot of exceptions to that. For example, in axis 2, we find dysthymia and we find social phobia, which have been characterized as much more personality-like in their structure. In axis 1 externalizing, we find antisocial personality. It's supposed to be an axis 2 disorder. It clearly loads with others, which we've certainly seen before. Where is borderline personality disorder here? Borderline sits intermediate between the axis 1 and the axis 2 externalizing disorder. There was a discussion over dinner last night. I've certainly heard bits of this before. Is borderline personality disorder really more personality disorder, or is it more an axis 1 condition? Manifestation. These results, with certain statistical caveats, suggest that it is literally a boundary, or remember, at the borderline, right? But in this case, of course, it's not with schizophrenia, but it's between axis 1 externalizing, the really bad acting conditions, the lay perspective, and the more traditional narcissistic, histrionic kind of axis 2 externalizing. So it's very interesting that it would behave in this way, but it gets even more complex than that. I have to point out a couple of other interesting things. Look at where eating disorder lies. Eating disorder is a combination of axis 1 internalizing and axis 2 externalizing. So what do bulimics do? Bulimics have a lot of anxiety, but they also act out in ways. And at least in my view, this, when we looked at this first statistically, this has an intuitive sense. At least probably one view of what the big structure is. The background, of course, is that for 150 years in psychiatry, we have been wishing to have a nosology that was based on
methodology. We don't. DSM is a historical descriptive document. And in fact, it's a document that's made up by committees, and the committees fight, and it's usually the alpha male or female on the committee who gets their way. Everybody beats their breast and says it's science. It's a little bit of science, but it's a lot of good process. We wish for the day where maybe from neurochemistry, maybe from imaging, or maybe from genetics, we'll actually be able to look at what the structure is. This is one of the first efforts to really see in a broad way what this means. Now, this is no means complete. We don't have schizophrenia, autism, bipolar illness, sexual disorders, so it's by no means complete, but it's not a trivial chunk of the important parts of psychopathology. Now, you'd think, and I have not talked a lot about what the environment is doing here,
But in this case, it's important. This is how genes act. This is how the environment acts.
very different. One thing we've learned, I haven't spoken about much at all, but every time we look at patterns of comorbidity, we can statistically test the question. Do genes influence patterns of disorders the way the environment does? The answer is uniformly no. And let's focus here now on borderline personality disorder. So where is borderline personality disorder? Borderline is here. From an environmental perspective, borderline personality disorder shares with other axis 2 disorders. And notice that environmentally, the axis 2 disorders almost all sort together. The internalizing and externalizing, which I would argue is driven largely by genes, is absent. Whatever the environment's doing, there's one general vulnerability that's pathogenic, increasing our probability of personality dysfunction. And borderline sits there. But borderline is the only one of the personality disorders that has got an important environmental link to axis 1 internalizing. So just think about the complexity of borderline personality disorder. So genetically we've got axis 2 externalizing and axis 1 externalizing contributing both to borderline personality disorder. Environmentally, we've got whatever's predisposing the environment generically to personality disorders, but what's special about borderline is whatever environmentally increases risk for major depression, dysthymia, is also increasing risk. So it sort of sits in this center of these various psychopathological processes. How do we do it? Yes, we put it all into a computer program and push a button, but of course that's not the answer. All right. Let's imagine for a moment that you and I are a pair of identical twins. I realize this is where we've been separated at birth and other things. I have two traits within myself. Okay, sorry. The question was, how can we really tell what the environment is doing here separate from what the genes are doing in this study of twins? Where's the magic, as it were? So this will be a test of my pedagogic skills. We'll see if this will work. So if you and I are a twin pair, and I have, let's take two disorders, major depression and generalized anxiety disorder, just because that's the easiest example. So I have major depression. And you share all your genes with me, but since you and I left home at the age of 18, my environment has been pretty independent of yours. If what makes major depression and generalized anxiety disorder a result only of our genes, my major depression will predict my generalized anxiety disorder and your generalized anxiety disorder exactly the same, because you and I share all our genes. On the other hand, if those two disorders are tracking because of environmental experiences, I had a much worse marriage, I went off to Vietnam, I had some other trauma, then my major depression will predict my generalized anxiety disorder much better than yours because you don't share your environment. That's really the basic logic. And then, of course, we add in DZ twins so we can figure out what is going on from just our environmental sharing when we grew up versus the genes we actually share. But it is that's the logic of these multivariates, just expanded out. It's really patterns of relationships within twins, cross MZ twins, and cross DZ twins that allows us to sort. Well, in this case, there's only 3 for the environment. And what they literally represent is commonalities across these conditions. So remember, factor analysis is roughly a data reduction technique. We have the correlations in the environmental exposures across all these disorders, and they can be most easily and succinctly explained by these 3 aggregate statistical term is latent variables. So it's telling us that there's some common process across all of these, with that number representing the degree to which this specific condition is related to this common factor. I think that's fundamentally it. They're sort of aggregate effects. Yes. Right, those were the identical latent constructs, but again, now we're reflecting what has occurred uniquely within an individual as opposed to what's causing resemblance across twin pairs. So what's hard for people to wrap our mind around, we don't actually go out and measure the environment. The environment is a latent thing, and it's essentially indexed, as I described before, by in what ways do I resemble myself more than what me and my identical co-twin resemble. Because if there's something within me that's much more similar than the person I'm genetically identical with, that has to be a result of my own environmental experience. Not in this study. Now you can add, and I will be showing you, we all can bear with us, studies where we've added environmental measures into these. But in the terms, statistical terms, these are latent. They're being inferred from the patterns of resemblance. And that's good because we catch everything. It's bad because we can't specify what's going on. So that's just the positives and negatives. Yes?
This slide is not in the make it
yeah, we'll figure out a way to do that. Right. Oops. All right, that is really the part I do on borderline. So I'm going to kind of segue back into where I was in genetic epidemiology and how we're doing for time. Okay, yeah, doing pretty well. So what I want to, we've spent a lot of time about patterns of comorbidity. I now want to take a very different approach and ask about development. And I would at least argue that this is certainly generically relevant to the processes of borderline personality disorder. We want to think about whether genes act dynamically over time or whether we can accept the more common, but I would argue generally incorrect idea that genes are static. There is a tendency in our culture, once you use the word genetic, to think that means fate. It can't be altered. There's no variation. But we know from biological studies that once you actually go into cells and measure how genes are being transcribed, that in fact genetic mechanisms are highly dynamic, shifting as a source of environmental exposures. I want to show you one design that tries to parse this question for development. And this is a study that I've done in collaboration with Paul Lichtenstein. This is a Swedish study. It's no accident that many American researchers have a long tradition of working in Scandinavia because of the excellent epidemiologic characteristics of their sample. These are about 2,500 twins that represent a complete birth cohort born in those 16 or 18 months between May of 1985 and December of 86. And what is particularly interesting about them is that this is a group that has been followed through what I would argue is the most dynamic developmental time in human experience, which is from pre-puberty to early adulthood. So think of the social and biological changes that occurred in humans as they moved from being 8 years old to being 20 years old, changing dramatically. This is a summary slide that is asking the following question. The variable that is being measured is anxiety and depression, as measured by Achenbach's CBCL, Child Behavior Checklist. And it is, in this case, elegantly being estimated from both reports by the parent and by the child. So we're sort of extracting out what is in common between them, which provides us a better aggregate estimate of actually what's going on. The question we're asking is, are the genetic influences on this critical trait developmentally stable, or are they dynamic and shifting over time? This curve, this sort of pinkish purple, represents those genes that are influencing anxiety and depression at the age of 8 or 9. And what we see, instead of those being highly stable over time, which is what we would expect if all gene action persisted without change over this developmental period, a rapid drop, so that by the time you're 19 to 20, the genes that were influencing your anxiety and depression when you were a prepubescent child are accounting for a very small portion of what's going on. Especially interesting is this huge surge of new genetic influences in puberty. We're not the first study to show this. Judy Silberg in our own Virginia twin sample has shown this as well. That is that puberty represents, both from a psychological, and a biological, and a genetic perspective, a real threshold. New things, new genes, new biological processes become turned on and active that were not present before. This would literally mean that if you were identifying individual risk genes in a 9-year-old child, and you tried to measure those risk genes again when that individual was in mid-adolescence, they will be much less potent on average in their risk. The factors are shifting. I would have assumed that that would have been all we detected, but in fact we found statistical evidence for a modest new set of genetic risks in mid to late adolescence and modest evidence for a late shift. So this is predicting a very dynamic pattern, shifting important. And by the way, if you looked at your serum cholesterol level, you have the same kinds of results. That is, the genes that influence, when estrogen and progesterone in women, and when testosterone in men get turned on, it produces a wide range of biological changes, including gene expression. So it gives you a picture that when we think about genes being static, being crusty, you're born with them, they stay there, that's not at all true. Gene influences are dynamic over development. All right, here's another look at what is, for me, a very interesting question, which is psychoactive substance use. What makes this interesting is this is kind of the paradigmatic complex trait in that we know, both from our, I assume, clinical work and our own individual experience, that substance use is a highly social phenomenon. You are introduced to the substances by friends and peers. You are encouraged in their use by friends and peers. Your genes for anxiety or depression don't need any special exposure to be developed. On the other hand, if you have genes for alcohol dependence and you never drink, those genes will be frustrated all their life. They're never going to get to do what they were supposed to do. And that's just the way it is. How does cultural and environmental factors interrelate with genetic factors in something as simple as cigarette use? So this rat's nest is collected in the following way. We went to about 1,800 male Virginia twins. We gave them what is called a life history calendar. We literally had a physical calendar that the interviewer had. And when were you born? When were your sibling born? Did your family move? We kind of dated the main developmental approaches. We did our interview, and at the end of the interview, we said, now, how old were you when you smoked cigarettes? How many cigarettes did you smoke that year? When did that change? And we track across their entire life, up until the current time, their own report. We know this is reliable. We think it's valid, but we don't have direct evidence of validity. Their average number of cigarettes they smoked over their lifetime, and this is what it looks like. So that's a fellow who smoked 5 packs a day and lived to stop at around 58. Notice this is Virginia, so we have this steep upsweep at about age 10, 11, 12. The average age of onset of smoking in Virginia males is about 12 and a half years old. Not familiar with that factor. And look at this mess. So the question is, what could you possibly learn from this? Well, the next question that at least in much of my life, a twin researcher, is give me the correlations in this between MZ and DZ twins. And this is what the statistician gave back to me. This is, in my eyes, beautiful. We'll see whether I can convince you of that. This is age here. This is correlation. These are dizygotic twins sharing half their genes in common, monozygotic twins sharing all their genes in common. We could get stable estimates around the age of 12. And what is so exciting here is that those first 3 years, when most kids are just learning to start to smoke, the MZ and DZ twins are absolutely on top of each other, which is what you would expect if social processes were critical and genes aren't doing the thing. Okay? Then what happens as more and more nicotine starts getting into the body, and you either start accelerating your smoking behavior, which is pretty typical, or you decelerate. The MZ twins keep getting more similar and stay stably similar, and the genetic differences of the DZ twins begin manifesting, and they fall to a lower level. So this is suggesting that drug abuse, in effect, is like a 2-stage rocket. You've got to get the cultural environmental exposures to get the substances into your body, and in that stage, genes aren't doing squat. And then, if you're genetically vulnerable, then you're going to kick off and move into a dependent state. Now, if you want to see it in prettier pictures, it looks like this. So What you see is genes play no role in nicotine intake, and then you can ignore these bumps. That's just stochastic stuff. That ineluctably and inevitably, once the drug starts getting into your body, the role of genes increase and the role of environment steadily decrease. If you look at alcohol, same picture. You look at caffeine, almost the same, but shared environment plays less of a role because everybody has access to caffeine. It's not, in soft drinks and others, it's less concern. Obviously, what I find exciting here, remember we talked about that very first example. Everybody thinks, oh, geneticists, genetics, you guys don't care about the environment. That's not at all true. And this is another example of how genetic design clarified the close interrelationship with substance use between environmental exposure and genetic exposure. And for this particular phenotype, it's pretty clear that the two interrelate in a critical way. Overdevelopment over time. All right, a whole other area, and this is even before we get into molecular genetics. How do genes and environment interrelate with one another? I'm going to take you through the two major approaches about how these may relate. The first is genotype-environment interaction, or I prefer the more descriptive term genetic control of sensitivity to the environment. I'm going to begin with the example of genetic risk for major depression and the impact of stressful life events. So this is a slide that it took about 150,000 person-months of exposure to assess in our sample to generate this slide. So that meant that we were interviewing 8,000 or 9,000 twins. You get 13 months of exposure for each interview, between 2 and 4 times over about a 10-year period to give us the data to make this estimate. What's going on here? This is the hazard ratio for the onset of major depression. So 1 means no excess risk, 5 means a 5-fold excess risk over baseline, 10, 15, 20. This kind of research, you can think of us effectively as our research team is somewhat like a vulture. That is the one that sort of circle in the desert and wait for people to stumble in. So literally, I guess this is slightly self-pejorative, but we really do follow general populations and wait for horrific things to happen to them in that study. And then we rate them very carefully. So this was developed by George Brown. I can give you the technology of it. This has got reliabilities 0.6 to 0.7. Not perfect, but pretty good. That this captures the level of potency of the stressor of the event. So a 4 is the worst thing that can occur to you in civilian life. These are the best metaphor is that we all have things in our life that give us our meaning, purpose, and structure. And these events take you by the lapels and shake you and turn you upside down. Okay, so this would be, my doctor tells me I have breast cancer. My 19-year-old child who's been the apple of my eye is arrested for selling cocaine. I know nothing about it. My husband, with whom I have had a loving and trusting relationship, I go to my doctor with my vaginal discharge, and he says, "Madam, you have gonorrhea." A parent who you know and love in their early 70s, quite alert, drops dead. So these are awful things that life spells sends. Zeros are no exposure. 1s would be, and we have books full of these categories, a modestly negative work evaluation, a $150 fender bender, and we sort of rate these all the way across. Now, what's critical here is using a method I don't want to go into detail now. We have ranked people as a result of their genetic susceptibility to major depression, with the orange group being those that have the most benign, well-adjusted, unemotional, good coping kind of temperament. And those in purple, the reverse, the most fragile, emotional, reactive kind of individual. Now, if genes and environment only added together, what you're going to see is just a series of straight lines. That is, bad environment's worse for everybody, but its impact is equal across. You don't see that. Instead, what you see is this fanning out. And the critical feature is the slope. That is that, for sure, well-adjusted people are more likely to get depressed when they're exposed to stress, but it's a shallow slope. It really takes a lot. That even under these horrific circumstances, there's only a 5-fold increased risk for depression in these really resilient, psychologically robust individuals. You take the most fragile, and it's like a steep cliff. That is, you're now getting up to 30-fold increased risk from those individuals. So the fundamental idea here is the following. We tend to think that what genes do is just make us vulnerable or invulnerable for psychiatric disorder. I am trying to convince you that's not the case. Importantly, what genes also do is render us more or less vulnerable to the adversities that life throws at us. And that is an important way by which genes end up contributing to psychiatric illness. I think that I am going to skip through this in the interest of time. All right, I want to show this slide because after I started showing these results, I asked myself, are there other things that can alter in a lifelong fashion your sensitivity to stressors? And I went back to a series of animal studies done both in rodents and primates that show, roughly speaking, that you do a variety of nasty things to either young monkeys or young rats, and then stress them as adults, that in some circumstances what you do is get a much more augmented stress response from those that have been stressed earlier in life. Now, we don't have such specific measures, but we did very carefully in studies of females assess childhood sexual abuse. We can go into that in more detail. It's tough, but I think we did as good a job as one can do in this situation. So what I asked, this slide looks a lot like the last slide, but here, this is a group that had no childhood sexual abuse. This is a group that had moderate levels, by which I mean they had flashing or they had breast being touched, but no genital contact. And this group, which we know is the most pathogenic, had attempted or completed sexual intercourse, typically on multiple occasions, unwanted before the age of 15 with all the other stuff. And they're now measured, they're on average over 30 years old. So these events have occurred on average 20, 25 years ago. But what we see, I find quite dramatically, is a pattern that looks a lot like what we showed for genes. That is that what this suggests, on average, is that childhood sexual abuse produces, at least per decade, if not lifelong, a relatively permanent change in your sensitivity to the pathogenic effects of stress as an adult. Just like those animal models. Whatever happens, the lack of trust, the disruption of ego identification, those processes of childhood sexual abuse render those individuals vulnerable for most of their adult life, much more vulnerable to the effect of subsequent adversities than individuals that did not. So again, an example that in this case, childhood sexual abuse and a genetic vulnerability look a lot alike in terms of how they change people and their sensitivity to adversity they experience. Okay. The second major area I want to discuss about how genes and environment interrelate is sometimes called gene-environment correlation. I suggest the more informative term, genetic control of exposure to the environment. Now, you're a mental health trained audience. Hopefully you will be fairly sympathetic to this idea. But one might imagine that most of what the environment does is just fateful. Right? There are environments, I'm driving down Highway 95, there's a truck in front of me, a big log rolls off the truck, I'm not talking on my cell phone, I'm coming to normal speed, I get into a bad traffic exit, I get some head injury. It's a fateful event. So there are things that are really just plain bad luck, fateful events. But a lot of what happens to us human beings, we play a role in creating, right? Because some of us drive faster, some of us talk on our cell phones, some of us use drugs a lot. Of course, how many of us have been in clinical situations, something like the following? You know, G-Doc, I was down at the bar, and this guy just turned around and slugged me. There was no provocation. He said, son of a bitch. And then 20 minutes later, it turns out that, well, oh, yes, I did insult his girlfriend, and I did say this. And so as the story unfolds, and I think you get the picture here, you know, we see people that have bad relationships. Sometimes they did just marry a son of a bitch, and that's the only explanation. But most of the time, it's more complex than that. Most of the time, there are dynamics, and that, in fact, we create our social world to a substantial extent. And the metaphor that I have often found useful here is that some people, if life is a lake, some of us are like canoes, right? We just these bare ripples around us. and others are like Mississippi riverboats, right? Just sort of storm of stuff as we go through life. And I think, again, clinically, the people who we see are more like the riverboats. The relationships are traumatic, their work problems occur. So is it true that the environment, that we are just passive recipients of our important psychosocial environment? I think even though when I was trying to publish these results 15 years ago, I got this terrible feedback about this sort of atavistic genetics, I think when you talk to clinicians, it's just self-evident that important parts of our environment are created. So if I were being more formal about it, old-fashioned kinds of epidemiology think that we are purely the passive effects of our environment. My genes contribute to susceptibility, and I'm just sitting there passively. Again, if I'm sitting there next to a lead-smelting plant and I'm breathing in the lead, that's right, I'm a passive recipient. But my brain has feet. I make behavior. I create my environment, my marital relationship, my relationship with my kids, my relationship with my colleagues, whether I drive safely. All of that has a lot to do with my own behavior, so that my brain and behavior influences the environment, but then feeds back on my susceptibility. So I sometimes like the term inside the skin gene pathway and outside the skin gene pathway. And of course, the physiologists think that the idea of an outside the skin pathway is ridiculous. They would make fun of us. So let me show you two examples. One is peer group deviance. Let me try to summarize what's going on in this slide. So peer deviance is a trait that we've got about half an hour more, and we're going to get into molecular genetics. We'll get you through it. So I realize this has been a pretty long talk. Peer deviance is the sort of thing that sociologists and criminologists love to measure. It would be, if I were to give you a questionnaire and say, between the ages of 15 and 18, I want you to enumerate for me the name of your 5 best friends. And then how many of those smoked cigarettes, used alcohol, got drunk, skipped school, used knives or weapons, sold drugs to younger kids, got arrested, etc. I think you get. Now, what we tried to ask in this study is what influences your peer deviance between the ages of 8 to 11, prepubescent males, all the way into early or middle. Now, think about what happens developmentally to humans over this period. When you're 8 years old, you can maybe get on your bicycle, but most of your friends are going to be within a very proximal block. You're going to the same school. Your environment is constrained. And one way of thinking about human development is that one progressively be able to create more and more of your environment as you grow. I think those of us that are parents in the audience, I certainly remember the time that I was standing in the driveway and my oldest child was driving out in a car for the first time, right? So I sort of experienced, oh my God, there are things I can't control. Her ability to travel and change things is out of my hands now. So that life, in some sense, increases our ability to create our own environment. When I move away from home, by the time I'm 25, I'm pretty responsible for what my social environment is like. So this study is addressing what drives that change. First, there's an explosion in variance. People become more different. And the key issue is that much of that, over time, is being driven by genes. Not all of it. Environment's important. I'm not claiming. But part of what I'm saying is that one aspect of development is our increasing capacity to influence our social environment. And what do we do socially? We like to associate with people like ourselves. So my genes drive my temperament, but then causes me to select into environments that are increasingly of my own creation. That's the basic. And this is reasonable empirical support for that model. So that's one concept of Maslowian actualization, right? My genes get to actualize, I get to hang around with the sort of people I really want and what these are. I think that I'm going to skip this. And this. Okay. All right, so let's now move on to molecular work. We've got about 30, 35 minutes. So we are now back into paradigm 3, and this is a very different kind of science. My goal here is just to give you a kind of sense about what this dynamo is like. So if genetic epidemiology that I've been talking about, which has been moving pretty fast, we've got bigger twin samples, lots more coming online, our statistical methods are improving, our computers are getting faster. So if that's traveling at the rate, let's say, of a high-speed Amtrak train, molecular genetics is like a jet plane. That is, the capacity to generate genotypes, to do sequencing, to study larger and larger and larger samples has been moving at a breakneck pace. So this is just to remind ourselves that the genes that we've been talking about in aggregate are actual physical things. They sit on DNA molecules. Our genome is about 3.2 billion base pairs long. They're organized in chromosomes that have locations on them. They have arms, a short arm and a long arm. I always remember the P arm because P is petite in French for small or short. And they have this funny structure of introns and exons of DNA. So we are now in the world of molecular genetics. So what makes genes variable? So if you took my genome and your genome and we lined them end to end, what we would find is that between every 600 to 1,000 bases, we would have one that would be different. So that means on average, we would pick any one of us, we'd have about 3 million places in our DNA where I'd have a different base pair than you would, on average. 6 years ago, we thought that was all the story. That was the sources of individual variants. Well, it turns out, and by the way, that's the difference here. So that, remember, DNA is made up of A's, T's, C's, and G's. These are the base pairs that make them up. Basically a 4-letter alphabet that spells out our genes. And that here, we have an A in this location versus a G. That is a single nucleotide. Polymorphism means variable. The word, if you want to be at all cachet, the word is SNP. You have to use SNP. And then when, of course, you're having a chip that assesses the SNP, you talk about your SNP chip. Got to get the language here. In addition to the variants, these single base pair variants, or SNPs, we now know that there are large segments, not 4 base pairs, but tens of thousands, that are actually more common. That I might have a variation in my genome of a block of 10,000 base pairs, and I have 4 repeats of that, and you have 2. I have 3, you have 1. I have 1, and you have a deletion. That whole chunk is missing. And that more of the variation in our DNA is caught up in these. These are called copy number variants, or CNVs. And we'll talk a little bit about that, and particularly the exciting data in autism and schizophrenia about the role of CNVs. Now, I want to give you one example where we have had real success. I am not in this talk, for lack of time, going to talk a lot about early linkage studies or candidate gene association studies, except to say that those have been disappointing paradigms. They have produced some results that are probably believable. Our research group have worked extensively on that. But here I'm going to show you only one example. And here, this is a success story, because one of the problems with traditional candidate gene studies, so what you do in a candidate gene study is you try to pick a gene because its physiological function is likely related to the disorder that you're studying. So I want to study diabetes. You don't need to be a genius to say, well, let's look at the gene that influences insulin. Right? I'm going to study heart disease. Let's look at the genes that are involved with metabolism of cholesterol. Those are real candidate genes because we know about the biology. Do we know about the biology of major psychiatric illness? And the answer is no. The drug company reps may tell you that depression is too little serotonin, and that's almost entirely hokum. They also will tell you, and academicians will tell you, that schizophrenia really is too much dopamine. That's 97% hokum. We have relatively little idea at a basic biological level what causes the major psychiatric disorders. However, when it comes to drug abuse, we have candidate genes that are as good as anything you can take in medicine. For example, there are genes that are involved in metabolizing alcohol. There's a major variant in one of those genes that produces flushing reactions in 30% of East Asians that is highly protective for alcohol problems. So about 6 years ago, when nicotine worked, interestingly, the politics of this is that the Cancer Institute first started supporting genetics of nicotine work, and then the Drug Abuse Institute decided to get on board. So now both fund, and actually NIDA now funds it somewhat more. So it was, again, not a Einsteinian level of revelation to say that we ought to look at the receptors for nicotine in the brain. There are a series of nicotine receptors. Nicotine is the addictive substance. What turned out was something that I think we can now say is as striking a success as we have seen in our field. This is now a year old, and this is now 6 studies. Ours is this one done by Sam Chen and our group, of variants in a cluster of nicotine receptor genes on chromosome 15, alpha 3, alpha 5, beta 4, if you need to know. What's surprising here is that every single one of these results is showing significances substantially. This is what the messy results look like. This is how you map genes. So these are the individual variants, the A's, T's, C's, and G's here. See that they're rather spread around from this alpha 5 gene. And in the alpha 5, I think it's in that exon, there's an amino acid change in gene. There are now 2 meta-analyses that are in press. One involves 140,000 individuals. Talk about a sample size. The other only 42,000 that show that that amino acid changing variant changes your risk for cigarette smoking with p-values ranging from p times 10 to the minus 42 to p times 10 to the minus 70. So, I mean, those of us that ever worked in science, you don't ever see values like that. That effectively means that there's no chance that that occurs randomly alone, that it's highly significant. So there are variants there that impact in important ways, and we, particularly Sam Chen, we are now taking, for example, this receptor, putting it into a frog oocyte, the human gene, and trying to understand how does the biology of that gene change after nicotine exposure. Now, remember coming back to this issue about outside the skin pathways and how hard molecular geneticists were accepting that? Well, guess what other disorder the variant in that gene predisposes to? And the answer is lung cancer. So now think for a minute, how does this gene actually work in its cause of lung cancer? And it works something like this. This is a variant. We actually don't know entirely how it works. We think that it both improves the hedonic effect of exposure to nicotine, more pleasurable, and reduces side effects. So that gene, therefore, increases the risk for you becoming nicotine dependent, which increases the risk of you going out into the environment, purchasing these little paper sticks full of tobacco, and then lighting them, and then about 200 to 350 times a day for the average smoker, deeply inhaling carcinogens into your lung day after day after day after day, thereby substantially increasing your risk for lung cancer. Now, if that is not an outside-the-skin pathway, I don't know what is. It again shows the potential complexity by which a molecular variant is not impacting on a disease in a biological way, but it's impacting on changing your brain to your behavior, out to the environment, controlling risk factors back to you, back to the cells in your lung, causing a disease. So it just shows you the potential subtlety of what genes can be doing for psychiatric illness in general. All right, so I'm going to review 3 major areas here, but I'm going to focus particularly on genome-wide association studies and copy number variants. I'm not going to talk about animal model systems. I'm not going to talk about pharmacogenetics or about methylation. So let's talk about genome-wide associations. This is certainly now the leading paradigm in molecular genetics. You take between 300,000 and now actually 1 million and soon 2 million individual markers and are able to interrogate basically 80 to 90% of genetic information in the entire genome except for rare variants. Let me show you, probably going quickly, the results is going to be more sensible. This is how GWAS, that stands for Genome-Wide Association Studies. If you want to be current, you've got to get with the jargon. And this, by the way, is called a Manhattan plot. It's called a Manhattan plot because I guess those would be the World Trade Towers. That would be the Empire State Building. Here we are laying the human genome end to end, from the top of chromosome 1 to the bottom of the X chromosome. This is a logarithmic p-value scale, 10 to the minus 5, 10 to the minus 10, 10 to the minus 15. Now, one of the greatest difficulties conceptually in doing this work is that we are performing in most studies about 1 million statistical tests. And what happens when you perform 1 million, remember, if you perform 100 tests, 5 of them will be significant at the 5% level by chance alone. If I do 100,000, that's 5,000 tests. If I do 1 million, I'm going to get 50,000 results that reach traditional levels of statistical significance by chance alone. So obviously using a P05, there's no chance I'm going to see anything. So what you see is this is the chatter of statistical background. A p-value of 0.0000001 in a GWAS doesn't mean anything, likely a chance effect. So it's a whole new world from what you've ever studied in your statistics. On the other hand, you can see, so background, this study is now almost 2 years old, organized by the Wellcome Trust. It was a coming out party for GWAS. This was the study, would this method work for detecting genes for complex disorders? And they picked 7 disorders, 1 psychiatric, and the other biomedical, coronary disease, Crohn's disease, that's inflammatory bowel disease, hypertension, rheumatoid arthritis, type 1 and type 2 diabetes. Was it going to work? They studied 2,000 ill individuals, used a common group of 3,000 controls. And what they showed is Crohn's disease was the poster child. It was about 6 or 7 highly significant detected signals, almost all of which were quite quickly replicated. Rheumatoid arthritis and type 1 diabetes have huge hits. This, by the way, is in the HLA region, autoimmune disease part. And type 2 diabetes had multiple hits. You will notice that there are 2 disorders that seem to have failed this current test. One is hypertension, and the other is bipolar. What are we now going to see for psychiatric illness? I'm going to skip here. All right, so what I want to present now, through Pablo Gejman's permission, there has been a joining together of the psychiatric genetics community, in part encouraged by NIMH, in part by an increasing consensus that the only way we're going to solve these problems is by collaborating together, because the sample sizes needed are so large, to form a consortium. And there's a whole series of acronyms. This is called the Psychiatric GWAS Consortium, or PGC. And that has work groups on schizophrenia, bipolar illness, major depression, ADHD, autism, and a cross-diagnostic subgroup. I'm going to show you the results of Freeze 1, the first set of the schizophrenia group. I participated in this. This is being shown with the permission of Pablo Gejman. This is now basically public access. This was first shown, this data freeze was last October. These results were first shown publicly in November of 2009. So how did this work? We tried to carry out GWAS studies on schizophrenia of European ancestry. We tried to contact everyone who we knew was doing such studies. They had to be studying schizophrenia or schizoaffective disorder. They had to be sharing de-identified phenotypic and genotypic data. They had to pass quality control measures, and the analyses were done by the group at the Broad Institute. This is the Harvard-MIT group who are at the cutting edge of this field. This is what the sample size looked like. So we are now studying over 9,000 cases of schizophrenia, over 12,000 controls. These are the different sample sizes where the results came from. So this is now a game of trying to find sample sizes adequate enough to detect very small effect genes. Oops. So let me show you, there are 2 charts, 2 plots here. This is the Manhattan plot, and I'll show you a large one in a minute. This is what is called a QQ plot. What's informative is if the null hypothesis is true, by which it means there's no genetic signal there. The line should lie along this dotted line at a 45-degree angle. Those few dots up here represent the individually potentially significant variants. Most people in the field have concentrated on those results. I am, and some of our colleagues, at least as interested in this large deviation from this expected line at lower levels of p-values, much more than you would expect by chance. I will follow up. This is what is now sometimes being called the genetic dark matter, or the polygene background of large numbers of genes of small effect that we know are statistically, we get a statistical signal in aggregate that they're there, but we're not able to easily identify individual genes themselves. I'll come back to this point. So this is what the full Manhattan plot looks like. We have excesses in HLA particularly. I'll show you these other regions here. None of them are currently in genes that would have been suspected to be involved in schizophrenia. This shows you how difficult this path is. This is characteristic of other complex disorders, where the variants that we find are not typically in previously suspected genes and may not even be in genes at all. Trying to understand the biology of the action. Now this is the odds ratio here. I defined that in the next slide from Dr. Friedel. We had to talk about this last night. Effectively, you can think about this as the proportional excess of caseness in individuals who carry that genetic variant. That means that this risk gene, if correct, increases the risk 19%. This increases 13%, 23%, 21%. Now, why is that very small? We know, roughly speaking, that if you are an identical co-twin of someone with schizophrenia, your risk of illness is about 100 times greater than the population. So those of you that are mathematically inclined, how many 1.2s would you need to multiply together to get to the number 100? And the answer is hundreds. So that's the first point that I will come back to in a minute.
One way to think about what psychiatric genetics has been through in the last 30 years is a declining set of expectations about the effect sizes of individual genes. So in the 1980s, I would have talked to young people who had found 6 pedigrees of bipolar illness and wanted to find the gene for bipolar illness, and then we're going to get their airplane tickets to Stockholm to get their Nobel Prize. The field was full of this excess enthusiasm that these methods would occur. And what we have, in essence, been learning through decade after decade is that first we could have found genes with odds ratios of 3. And then if they were 2 or above, we could have found them. Then if they were 1.6 and above, we could find them. And now we're at the point of 1.2, 1.15, 1.1. So the lesson has been more a negative lesson, which is that at least with any frequency or commonality, I will show you slightly contradictory data in just a moment, common genes that robustly predict the risk for psychiatric illness do not appear to exist. And that the genetic signals that are there appear to be a result of aggregate effects of fairly large numbers of individual genes, which themselves each have quite small effects. That appears to be the current message in the field. All right, I'm actually going to move through this pretty quickly. All right, so what are the sort of patterns that we're seeing in other results? So I'm halfway through my closing comments. First is that we're going to see lots of heterogeneity of mechanism. If we look, this is a slide on what has been found for type 2 diabetes, the diabetes of adulthood that's associated with obesity. And do you think that the genes we're finding is in one pathway? The answer is absolutely not. We're finding genes involved beta cells or the cells in your pancreas that make insulin. So some of the genes that impact on your risk for type 2 diabetes are involved in beta cell formation. Others are involved in the beta cell secretion. Some just control your fasting blood glucose. Others increase your being fat. Others impact on your fat cells. Others regulate insulin pathways. And of course, although the pancreas and the control of sugar is very complicated, compared to the human brain, it is child's play. So if we think that this is complicated, I don't think we can begin to appreciate, if we are in 5 to 10 years in a position to show you something like this for schizophrenia. Are we going to find something that involves only one individual system? I think that that's highly unlikely. The evidence suggests that it's going to be very complex and multifactorial. Similarly, remember I showed you all those slides early on that genes don't respect DSM. Well, they don't respect medical disorders either. Because what we're seeing is that individual genes can be predisposed to a whole host of different cancers. Not surprising. Genes for prostate cancer, lung cancer, pancreatic cancer. Genes that are involved in autoimmune disease. There are common genes that are showing up for rheumatoid arthritis and asthma. Right? So as we begin to look, we're seeing that genes don't respect individual disease boundaries. The things are commonly very complicated. Individual genes, technical term is, are pleiotropic. They impact on many different things. So our hope that we're going to have this very pretty one-to-one matching of diseases to genes, not in this world. That's just what the data is suggesting. All right, this is an important slide. This is work by Sean Purcell. And we'll see. It's getting late. Let's see. Remember that QQ plot where that curve curved up way far away from the 45-degree angle? So Sean Purcell tried to actually test whether there is, in the schizophrenia GWAS studies, evidence of an aggregate genetic signal that you couldn't specifically detect by individual genes. I'll try to explain what he did. He began with about the 50,000 independent regions in the human genome that are not correlated. He did that for statistical. And then he basically took a marker of each of those 50,000 little blocks, compared the schizophrenics and the controls, and every time that variant, one was a little bit higher in the schizophrenia, that goes into the bin of making this polygene score. If that one was lower, it takes the flip sign and goes into the bin. It goes down to 10,000, 20,000, 30,000, 40,000 individual gene variants making this overall score. So he gets this score on one sample, and then he says, all right, I'm going to go test this on another sample of cases and controls. And is this aggregate measure of risk across these tens of thousands of genes going to successfully differentiate my schizophrenics from my controls? And what he showed here,
This is taking the top 10% of the SNPs, 20%, 30%, 40%, 50%, when he was testing this score generated on one sample on another sample. He found a p of 10 to the minus 28. So this polygene score, even though we're talking about thousands of individual variants, is to an extraordinary statistical extent being able to identify a new set and differentiate schizophrenics from the controls. And what is even more mind-boggling is that when he went from 10 to 20 to 30 to 40 to 50% of the variants, the signal kept getting stronger. So it's not that there's a few hundred genes packed off into that tail. The further back you go, the more and more robust the signal gets. This is, used in 1960 expression, mind-blowing in terms of its potential implication of the number of gene effects. What else did Purcell do? Well, he went and tested this on a whole bunch of medical disorders. Coronary artery disease, Crohn's disease, hypertension, rheumatoid arthritis. It didn't index at all. This is not something generic. This is not a methodological artifact. He tested it on another sample of schizophrenics that was smaller, a huge signal. Then, again, mind-boggling. These were both European samples. He tested it on a sample of African-American schizophrenics, and the signal was remarkably weak. We don't know much. There certainly are a number of samples in African-Americans, an increasing sample in East Asians, but we are pretty clueless at the level of genetic sharing of risks across major ethnic groups in the human evolutionary tree. If this is right, it's not been replicated, it is dramatically suggesting that the risk profiles are going to differ big time across ethnic groups, as if we didn't have that problem. This is another major issue. Then he tested it on bipolar illness, and you get a signal that's quite robust, not nearly as strong as schizophrenia, but it's certainly suggesting some sharing. We've been extensively involved in simulations of this. We know that this does not have to be artifactual. That is doing, when we predict what we expect is going on genetically, we can certainly reproduce these findings. It may be that this is some of the most important results to come out of GWAS. Not what was predicted, and everybody wanted to find genes, published a paper in Nature, applied for the Nobel Prize. That's the sort of standard. It could be that this background signal is really going to be more important. And this, of course, if I'm trying to do genetic testing, trying to do predictions, it may be that we're going to have to get aggregate predictions across hundreds, if not thousands of genes, rather than the 1, 2, or 3, quote, schizophrenia genes that will guarantee the tenure. This is still early days yet. All right. I'm going to briefly talk about copy number variants and then going to close. So copy number variants are these big hunks of genome that differ. This was begun by Jonathan Seabad, who works at the Cold Spring Harbor Laboratories, which was then directed by Jim Watson, the co-discoverer of DNA. Jim, by the way, has a child with schizophrenia, and he remains in his early 80s actively involved in schizophrenia genetics meetings and knows all about the literature. Is that they began by trying to look at these large copy number variants, and Seabad's group produced several months earlier a paper that electrified the field showing substantial excesses of these kind of copy number variants in autism. He followed this up with the first study finding these modest excesses of aggregate effects between 5% in controls and 15% in cases of these large hunks of genome differing. And I'm going to just skip to this overall slide. Every study, there's now been 8, find excesses of copy number variants in schizophrenia, but they're all individually rare. A typical finding might be 8 of the deletion of this hunk of genome in 3,000 schizophrenics and 1 in 7,000 or 8,000 controls. That produces odds ratios of 4 or 5 or 8, much, much, much larger than we're finding with the individual variants, but for a very small group of people. The deep debate within the field in schizophrenia is this an important insight into the biology of schizophrenia? Or is this basically, if you randomly shake up the human genome and brain development, you predispose to schizophrenia? So CNVs are not surgical single bases. They're often dozens of genes. You're just taking a whole hunk of the genome and either duplicating it or pulling it out. So one metaphor is, those of us that are old enough to remember before all of solid state, when there actually were wires in the back of things like televisions, right? So a CNV is a little bit like reaching your hand in and yanking out a bunch of wires from the human genome. And is that something specific about schizophrenia, or is it very non-specific? Most of the studies that have followed up the schizophrenics with large CNVs, they tend to be mentally retarded, they tend to have epilepsy, they tend to have wide-set eyes. Maybe these are more mental retardation syndromes. This is hotly being debated about whether CNVs are going to be very specific guide to the etiology of schizophrenia, or where they reflect much more non-specific disruptions of broad pathways. This is just a slide showing you the commonality of CNVs, because there's some that are the same in autism and schizophrenia. The ones that are for autism spectrum disorder are red, schizophrenia is blue, and black, particularly this area 15q, are combined between the two of them. So I think it's really time to sum up. Any of you that have any intellectual energy left, I realize I've covered a long way. So what's the overall conclusions here? All major psychiatric and drug use disorders are heritable, although the degree of genetic influences differs substantially across disorders. Genes do not, by and large, respect DSM-4. For most disorders, gene action on psychiatric disorders is not static, but rather is developmentally dynamic. For many disorders, genes and environment do not just add together. Rather, genes influence sensitivity to the pathogenic effects of environmental stressors, and they influence the probability of exposure to high-risk environments. Efforts to identify the genomic location of specific risk genes for psychiatric disorders by linkage and candidate gene association have met with rather limited success, with the probable exception of drug use disorders. Replication has been a major problem. We now have powerful new tools, especially genome-wide association, copy number variants, and bioinformatics, which I did not talk about. Whether these methods will allow us to identify replicable risk genes for psychiatric disorders is still unclear. We will know a great deal more in the next 2 to 3 years. Current evidence suggests that psychiatric disorders are highly polygenic, with many genes of quite small effect size and some rare genomic events, particularly copy number variants, of moderate to large effect. A major question remains is the likely great heterogeneity and complexity of the neurobiological basis of psychiatric illness. Discovering risk genes for psychiatric disorders is not purely academic, again in the pejorative sense, as they provide the best chance we have for understanding the biological substrate of these disorders and identifying potentially new drug targets. Let me just take a moment on that before I close. I began my psychiatric training in the era of the one neuron model of psychiatric illness. So I used to have the job of taking little vials of cerebrospinal fluid that Malcolm Bowers was studying and trotting across the hallway at the Connecticut Mental Health Center to our GC mass spec, because we were going to show that schizophrenia was all the result of too much dopamine somewhere in the brain. That paradigm has failed. The techniques that we currently have available, be they very sophisticated, by studying blood, urine, cerebrospinal fluid, we've not been able to track. The disorders are too subtle. They're manifesting too small numbers of neurons. Almost everyone in the field believes that if we are going to crack the biology of these conditions, it will be from things that I showed you here, from DNA variants, back up through proteins, which genes make, back up through physiological pathways to drug discovery. This is not something that is only an academic thought. 8 or 10 years ago, when we were a little bit in the first bloom of gene discovery, I had a person high up at Merck Pharmaceuticals who said, Dr. Kendler, 2 weeks after you or any other scientist publishes a credible gene discovery in schizophrenia or depression, I will have 700 scientists working on trying to take that gene discovery and move it into a patentable molecule that we can bring to market for a symptomatic disorder. We like to pride ourselves on the developments in psychopharmacology. The dilemma is that with a few small exceptions, naloxone treatment of alcohol being one, the drugs that we now use have been found by accident. We have not, in almost all situations, been able to develop drugs based on an understanding of the pathophysiology of the disorder. What is most important about what I've spoken about today, from the perspective of molecular genetics, is not these theories and not these odds ratios, but that they're going to provide targets. And you think, well, we've got these little genes. How can those genes be important? Well, Ed Skolnick, who's got bipolar illness family, who was the chief medical officer at Merck, who decided to quit in his mid-50s and go work at the Broad and discover genes for psychiatric illness, tells the story that the discovery of the statins, which which are the most widely used, and probably the kind of drug that has had the biggest aggregate effect on public health throughout the world, was discovered through a tiny gene effect on that. So it doesn't need to be the big gene. It needs to be a pathway that we identify that can tell us something about the biology, that you can get a small molecule safely into the brain that isn't toxic. And we cannot predict ahead of time. We may be finding dozens of those individual ones. We don't know which one's going to be the target. But the chances that one of them are represents one of the most important things that this field represents.
So the closing point is that once we discover these genes, from a research perspective, what we then want to do is to trace etiologic pathways. I want to be able to do studies like I talked about, not only with twins, but identifying individual molecular variants. How does that develop over time? How do those interact with your environment? To begin to develop realistic etiologic models, being able to specify individual genetic risk factors. Whether I will live long enough to do that or not, I don't know, but that's certainly where I'd like to aim and end up. Now, I've presented a lot of results here. I have done virtually none of the statistical analyses here. This is a very large team of dedicated individuals, most of whom work about 500 yards in that direction at the VIPBG under the sustained sponsor and leadership of my chair, Joel Silverman, who introduced me this morning. But I also have good colleagues now sprinkled throughout the world, Paul Lichtenstein in Sweden, Ted Reichborn in Norway, that produced this data. This is a key group of investigators. Dawn Thistleton is sitting somewhere in the audience here working in our molecular team. And there are many other names here that are not all represented. These are the people who have supported this work. I have no conflicts of interest to declare. I don't work or relate to pharmaceutical industry. Those of you who wish to know more about the work, this was a book that was published about 3 years ago that described in detail the twin investigations. This was written for a lay audience, so we try to go through the statistics gently. Some people think we've succeeded, some less so, but this will certainly give you a lot about that. And this was recently published just about a month ago, co-authored with Jonathan Flint and Ralph Greenspan, trying to give a general background, more on the molecular end, but combining what we know about human beings and about rodents and about fruit flies in what I think is it's supposed to be a highly accessible way. So you've hung with me. I'd like to thank you for your attention, and this concludes my talk.